about some mean position, angle can also change. So when we talk about angular SHM, it can be understood as a modification to linear SHM. Replace x by angle, force by torque, linear acceleration by angular acceleration, mass by moment of inertia. Some symbols won't change. Delta would remain delta. Omega will remain omega. This is where you have to be very careful. This omega is not the omega of circular motion. This omega is the angular frequency of SHM. So in case of angular SHM, if I want to emphasize on, say, angular velocity, then I would be using a different omega symbol. There is one more symbol for omega, which is somewhat like this. This is where you have to be very careful. And then all other things work out very easily. Force is minus kx there in linear SHM, and torque is minus k theta here. Minus sign just shows that if theta tries to increase from the mean position, torque tries to decrease it. Omega. Omega is root k by m in linear SHM. So it would be root k by I in angular SHM. The equation of linear SHM is x equal to a sine omega t plus delta. So here it is this. If you want to find the angular velocity, the big omega, then differentiate this and it's done. If you want time period for angular SHM, 2 pi root m by k for linear SHM, this for angular SHM. Then comes potential energy, half kx square in linear SHM, half k theta square in angular SHM. Kinetic energy, half mv square in linear SHM, half I omega square in angular SHM. But which omega? Angular velocity omega. Total mechanical energy, sum of these two. And we know that the total mechanical energy in linear SHM is half k a square. So here it should be half k theta naught square. So easy if you follow this approach, synergy approach. When we talk about simple pendulum, that is the most common example of angular SHM. There's a thread, there's a small bob, light thread, we ignore its mass. If it is moved a little and released, and if you ignore the effect of air resistance, then it would just move on and on and on and on. Theoretically, it will be forever, but practically there is air, so it would stop, but we would ignore air for our derivation and for our discussion. Let's say when it is pulled and released and it is moving like this, at some instant its position is this, making angle theta. What are the forces acting on the bob? mg by the earth, tension, string, and that's it. We are ignoring air resistance. We need torque. About torque, trying to turn it towards this mean position. Let's say the length of the string is L. This point, let's say, is O. Torque about O tension is passing through O, so tension will not apply any torque about O. mg into this perpendicular distance, strictly speaking it is this perpendicular distance, but this perpendicular distance is same as this. So mg times how much? L sin theta. That's it. That's the net torque about O. Now clearly, this torque is trying to turn it clockwise. Theta is this. From the mean position, it is anti-clockwise angle. Torque is trying to turn it clockwise. So they have opposite sense. I have not put minus sign. So you can take it that I am dealing with mod. But direction wise, if you want to write, theta and torque are going to oppose each other. Now this is not SHM, I mean angular SHM, because this condition is not fulfilled. So generally speaking, we cannot say that simple pendulum will always perform SHM. However, if theta is very small, something like less than 4 degrees, in that case, and if it is in radians, theta is small, it is in radians, in that case we can make an approximation. We can take sine theta as theta. So we get this. Now we find it is working. It is indeed angular SHM. Direction point we have already discussed. So there is a negative sign if you are considering opposition. This is K, and the time period of oscillation would be equal to 2 pi root moment of inertia divided by K. We have said that string was light. If something is light, it won't have any moment of inertia. If string is not light, then it is not simple pendulum. Then it is called physical pendulum. Physical pendulum means anything which is heavy that can oscillate. It can be a rod, it can be some other shape, but that is physical pendulum. Here we are ignoring the mass of the string. So I is just the moment of inertia of the bob, and we are going to consider bob as very, very small. So if it is treated as particle, then its I is simply mass times L square. If bob is not a particle, no problem. We can handle that case, but that case will fall under physical pendulum. In case of simple pendulum, bob has to be very small. ml square upon mgl. And you are seeing a familiar result equal to 2 pi under root of L by G. Sometimes, in fact, I think for many, this is used in laboratory, school laboratory, for calculating G, small g. So you would perform an experiment taking a simple pendulum. You will measure time, capital T, using stopwatch. You will measure the length of the string, or length of the string would be given to you. So you would measure T, you suppose know L, and you will find G. In that experiment, you are bound to find some errors, because we have in our derivation ignored any air resistance. And no matter how good the conditions are, air is going to be there. We have ignored the moment of inertia of the string. We have taken it to be massless. That is not possible practically. So no matter how light string is given to you in your laboratory in the school, it is going to have some mass. You are not going to get accurate answer for G. Now what is done in that experiment is that since angle is very small, you shouldn't be taking large angle. You shouldn't be taking large angle, because then again in our derivation we have assumed angle is small. That is okay, you can control that. But then for one oscillation t will become very small. So your error of measurement will be more. If you try to measure exact one value of t, one single oscillation, time taken for one single oscillation, if you try to measure using stopwatch, then you will make error in that. So what is done is that you wait for 10 or 20 oscillations. So you press your stopwatch when it is, say, at one extreme position or one middle position, and then keep on counting oscillations. Maybe after 20 oscillations you find the total time, and then that total time you divide by 20. That is the way to do it. That will give you much better answer. But in spite of all these things, as I told you, there are going to be errors, and you may get incorrect value of G. There is an alternative treatment to arrive at the result for T, for simple pendulum, and that treatment takes the motion to be strict. Now, is it good or bad? Here we said theta was very, very small. If theta is so small, up to 1 degree, 2 degree, 3 degree, 4 degree, then actually the curve looks like a straight line almost. So while in this drawing it may look like a clear curve, but that's because theta is big, that I have shown. If theta is small, it would almost look like a straight line. So that treatment can be called as simple pendulum, as maybe linear oscillator, linear. It's considered to be performing linear SHM in that case. So you just take it as X and you follow the force approach. You talk about the restoring force in that case, rather than torque. So you break mg into two pieces, one towards the mean position, other one along the string, other one along the string. So if this is the instantaneous, in drawing I will have to show it big. If this is the instantaneous position, then one breaks mg into two components, one along the length of the string. Now the component which is along the length of the string, is it correct to say that it will balance tension, or that's not always true? What would you say? One component is this, other component is this. This is theta, so that is theta. Yes, what do you say? Is it always correct to say that mg cos theta will balance T, or some better statement than that statement about mg cos theta? And the answer is no, it is not always correct. The reason is centripetal force. Who will provide centripetal force? So actually, T should be larger than mg cos theta. So T minus mg cos theta, that can provide the centripetal force. But there will be 2 points in its journey. There will be 2 points in its journey where this will be true. Can you tell me which are those 2 points? Where it is correct, when it is correct to say T is equal to mg cos theta. That's right. When the speed is 0, then you don't have any centripetal force requirement. mv square by r is 0. And that happens at the extreme position, extreme right, extreme left. So in those positions, T balances mg cos theta. But everywhere else, T should be more than mg cos theta. So here we say that mg sin theta is providing the net force, net restoring force. And then we say the usual thing, let theta be very, very small, let it be in radians. So sin theta becomes theta. So you have F equal to mg theta. Now, whatever is there along the length of the string, that fellow cannot provide restoring force. Direction is 90 degrees. So then you say that theta is x by L. Straight line and arc are almost similar because angle is very, very small. mg x by L. And this fellow is k. Now you can complete it on your own. T equal to 2 pi under root of m by k, and you will find the very same answer. Now what happens if this pendulum is kept inside an elevator? Let us say this is the elevator. Either I say pendulum is kept, or maybe I can hang it right from the top, like this. What happens to the time period in this particular case? Elevator could be going up or it could be going down. Actually, going up, going down is not the key. If it goes up or it goes down with constant speed, nothing really matters, because it is the force that matters, and if it is constant speed, there is no force. But if it is accelerating, then it matters. So if it is going up or going down with constant speed, no change in the answer. 2 pi root L by G, same. If it is accelerating, whether going up or coming down doesn't matter. Accelerating up, it will matter. Accelerating down, it will matter. Accelerating down can also mean going up or going down. If it is accelerating up, then place an observer inside the elevator. That observer would say that there would be two forces downwards now, mg also and ma also. Effectively speaking, g has become g plus a. That's it. So 2 pi under root L by g plus a. That is when acceleration is upwards. Motion could be upwards or downwards. Then how about accelerating downwards? If acceleration is downwards, then our observer, our non-inertial observer, would apply an upward force ma. So the net downward force will be m bracket g minus a bracket closed. It is as if g has become g minus a. So in that case, g is replaced by g minus a. So 2 pi under root of L by g minus a. Done. In these cases, there will be SHM. T will change. Then how about right side acceleration? Maybe now it is some car. Let us say it is a car. It is in a car. That is the roof of the car. Car going to the right, going to the left, doesn't matter if speed is constant. If speed of the car is constant, it doesn't matter. Because if you place your observer inside the car, then no zero force if speed is constant. So going to the right with some speed, going to the left with some speed, as long as the speed is constant, would not change the time period. It will be vertical only and will go to and fro as it normally does. But if you accelerate, no matter where the direction of motion is, if you accelerate, then even the equilibrium position will change. And that is because now you need to apply pseudo force. I mean the observer who is inside, that observer needs to apply pseudo force. So if this is the normal mean position, that normal mean position would not be the mean position anymore because of the pseudo force. What is special about the mean position in SHM? The answer is force. Force is 0. At mean position, force is 0. If that is the mean position, then I don't see how force is becoming 0. mg is acting downwards, tension is acting upwards, and pseudo force is acting leftward. How can this leftward force be cancelled? There is nobody to cancel the leftward force. So this cannot be mean position. Mean position is the one where net force is 0. So let us say mean position is somewhere here. Now, can that be possible? Let's see. Now what happens? Pseudo force left, gravitational down, tension here, very much possible. Three forces like those can certainly cancel each other. Break tension into two pieces here and here. One piece can balance this mg, other piece can balance this pseudo force. Done. That is very much possible. So at this position, there is no net force at all. Just like the vertical position in a non-accelerated car, it is just like the vertical position in a non-accelerated car. So you have a slanted position as the mean position. SHM is about that slanted mean position. It may look somewhat awkward, but that's how it should be. Somewhat like this. So what about the time period? Time period of oscillation in that case. The time period of oscillation has this result. Tension does not come in this. What comes is G, which is external to it, external to the bomb. Tension doesn't come in this. Here we would expect that the two external fellows, leaving tension aside, the two external fellows are mg and ma. When the only external fellow was mg, then g came. When there are, I'm not talking about tension. Tension is anyway not coming here. So when there are two external fellows, mg and ma, so shouldn't their resultant come as far as acceleration goes? Now A is in this direction, in fact ma is in this direction, mg is in this direction. So their resultant would be as far as force is concerned is this, and as far as acceleration is concerned is this. So T should be 2 pi under root of L divided by under root of G square plus A square. So often the result 2 pi root L by G is memorized as 2 pi root L by G effective. In normal usage situation, G effective is G. In case of elevator, accelerating up, accelerating down, G effective changes appropriately. In case of car, accelerating right or left, G effective changes accordingly. If you take pendulum at the top of a tall mountain, then G changes there, so T will change. If you take it inside some deep mine, then because G changes there, T also changes. While pendulum is perhaps the most common example of angular SHM, there can be several other types of problems relating to angular SHM. But let's begin with simple pendulum in application. One meter is right. If you would like this to be discussed on the board, raise your hand. Fine. Looks like a very bad clock. Yes, 28.8 minutes. You have seen in the previous question that time period should be 2 seconds for such clock. In place of 2, it is 2.04. That means for every 2 seconds, there is a delay of 0.04 seconds for every 2 seconds. So every second there is a delay of 0.02 seconds. You know how many seconds are there in a day? So in one day you will find 28.8 minutes delay. If you have any questions, then let me know. When do you think tension is maximum? When cos theta and v are the two variables. When theta is maximum, v is maximum. Do they? No. Cos theta is decreasing function. When theta is minimum, v is maximum. So 0. So when theta is 0, tension should be maximum. And if theta is maximum, v is minimum, so extreme, t is minimum. That can be taken as hint or clue. Mean position, tension is maximum. Extreme position, T is minimum. Mean position, T is maximum. Extreme, T is minimum. This is your assignment question. We stop now.